Nothing like a breakfast of M&Ms. That's for the day. It's that kind of day. You would think your alarm going out at 5 would be early enough, but it isn't.
My alarm always goes off at like 6, and I don't actually get up until like 7 every day.
All right. Wait a minute, what? How do you get here by then?
Huh? Because I speed here.
You speed here.
You know, I want to call complete total bullshit on all the people that are like, I started waking up at 5:30 and it changed my life for the better. I've been waking up at 5:30.
Oh, did I miss yours? I was going to say this didn't seem like a... Yeah. Yeah, there's nothing good about waking up early.
I'm just more tired.
All right. Thank you for the tests. I will get these guys graded. It's not like there was a mix of reactions to the tests. We'll see how everything goes. We'll see what people want as far as like a retake. That's what a retake, a points back type opportunity. I don't have problems with doing that in a class that's this small. Anyway, okay. But last time we met, we were having fun with set and set theory and set notation and so on. And hey, I remember now. I have a bunch of stuff. Oh, I have a grade, but I don't know that I wrote down. I'm not sure I entered the grades. That was what I was going to double check. Let me at least put it on the to-do list here to remember to check, because I don't think I wrote your grades down. I graded the papers in study hall yesterday, but I don't think I wrote them down yet in RDS. Did I write down the homework 7.1 in Finite Math grades in RDS? I will check on that when I get upstairs. So I don't want to get back to you yet in case. But you guys all did fine. I don't think there was anybody who systematically wasn't understanding sets, unions, intersections, things like that. No big deal. There was one question that I didn't grade just because it was kind of a mess. The one that was asked about set builder notation. That's not a standard term. That's a term that the book came up with, as far as I can tell. But that was like when your set A is, it's the values of x such that x is or I don't think they would necessarily have to do that. X such that that is integers greater than 10 or something. Okay. The point is, it's this notation of like, rather than listing them all out, you sort of wrote out the rule. Okay. Obviously, that's important in mathematics when like your set is maybe all of the prime numbers, or your set is all of the numbers, the Fibonacci sequence, or it's real numbers greater than 0, or something like that. But that's not really the direction the book is going with this, and I'm not sure why they introduced this strange term, set builder notation, only to walk away and never need that again anyway. So I don't really know what the point of that was. So I didn't grade that question because people, it turns out if you went to the index and just looked it up, it pointed you to exactly the page where they defined that term, but it wasn't that big of a deal. All right. On Monday, we had some fun with Venn diagrams. But I don't know that there's really any point in an explicit homework set about them. Because other than the fact you'll all get like hundreds on it, which is nice. But my guess is you're busy. We don't need to spend just huge amounts of time on that. Where we are going with all of this stuff about sets and notation and so on, is that now we're learning about probability. And probability is fun. The folks in quantitative reasoning just got done with probability. And they had fun with it, I think, as much as the guys in quantitative reasoning have fun with anything, and they're generally crappy about having to be in a math class. But, fortunately, we don't need to spend a lot of time on the basics of probability, because you guys are, survivors of other classes where you've already seen this idea about probability. And when we are studying probability, the beginning of a chapter of probability always, no matter what textbook you're using, always gets bogged down in a bunch of definitions, where they start talking about things like an event. Or they start talking about, let me throw some of the other vocabulary that they're doing up here. An experiment, a trial, an outcome, a sample space, an event, a impossible event, a simple event, mutually exclusive events. And here's the deal. Then you grab a different textbook and they use slightly different terms for this or whatever. These aren't like standard terms necessarily very well used in like statistics or something like that. But the general idea of like an event being something like an outcome or something like that is the main word that we need to worry about here. So like for example, we're going to be drawing a card from a deck of cards. I actually had a deck of cards here the other day and then they were in my pocket and I went home and they were still in my pocket and they're sitting out on the kitchen table. I forgot to bring them. So I was going to use the deck of cards, but you can picture, here's a deck of cards, right? Okay, the right word is that we're going to conduct an experiment here. We're going to draw a card, okay? And the outcome is we got the 7 of spades. Or the event. The event that is like, what are we trying to do? What is the probability the event is we draw the 7 of spades? Okay? So just don't be overwhelmed or intimidated by that vocabulary. It kind of just means what it sounds like. Okay? The jargon isn't that technical here. Alright, so like for example, we might talk about the probability that we get the 7 of spades. Now, it's not so hard to figure this out in kind of an intuitive sense. I mean, you already know how many cards in a deck of cards is the 7 of spades? There's only one 7 of spades in a deck of cards. This isn't some weird deck of cards like Uno or something like that where there's all kinds of weird cards and some of them have multiples and so on. No, there's only one 7 of spades in the deck of cards. And how many cards are in the deck of cards? It's 52. That might not have been something you knew off the top of your head. If there's anything about decks of cards you don't know, like, that when we're talking, by all means, just let me know. Because I know some people don't play a lot of cards. I mean, that's just not their thing. So our probability is 1 over 52, or 1/52, which works out to about 2%. Notice what we did without even really thinking about it all that hard. The numerator here is ways the event is a success. In this case, there was only one way the event was a success. If the outcome we're looking for is we're getting the 7 of spades, there's only one way that can happen. And the denominator of the fraction is ways the experiment can, I think the word the book is using is experiment. Ways the experiment can go. Whatever. I can't spell today. Alright. Well, there's 52 different possible outcomes. So the probability then is 1 over 52. Now, buried in this is an assumption that we're not going to get just too bogged down on, because this isn't a class on probability or course on probability or whatever, but it is hidden in here that every outcome is equally likely. Okay? It isn't like, for some reason, like maybe the cards are sticky and we're actually not that likely to get like maybe the ace, the 7 of spades is stuck to the back of the king of hearts, and it's not very likely when you pull it out you're going to get the ace, the 7 of spades. We're saying they're all equally likely. Okay? Same with like, you'll have experiments where, I mean, there'll be like problems that's, you have 8 balls in a bucket and 3 of them are red and 5 of them are blue. When you reach in, what's the probability of getting a blue ball? Okay, they're not saying for some reason you're like more likely to get a blue, like as in you're saying each of the balls is equally likely to be drawn. It's not hugely difficult to change this for when they're not equally likely. Like if for some reason some outcomes are more likely and some are less likely, but we're not doing that. That's not the direction we're going with this. So we can have all kinds of problems that are these simple events. A simple event is just sort of you're just talking about one thing happening. What is the probability that you'll get a spade when you draw the card? The probability you'll get a spade, well, there are 13 spades in a deck of cards. There are 4 suits, and each of them has 13 cards. So there are 13 ways that this can go right over 52 ways of drawing the card. So that happens to work out to, unsurprisingly, 1/4. Simple events like this are not really very challenging at all. I mean, once you have even the basic idea of how like probability works and so on. In fact, basically, this is all pretty straightforward. Now, things get a little bit, well, not that hard. Let's let's do some notation here just to make things a little bit less righty-outy. Where is an E as in an event? Like our event is drew a spade. So you're playing cards and you got a game here where you're just trying to say what is the probability of E, where E is I drew a spade. So then we just did that one there, that the probability of E is 1/4. And we can stick with the notation that we used in the set theory stuff, where we used a apostrophe to mean the complement of this. So this would be drew anything but a spade. Remember, complement here in the sense of it completes. It makes, there's a universal set here, all the different possible things it could draw. We are now taking the complement of drew a spade. We drew anything but a spade. And the probability of not E will just be 1 minus the probability of E. Notice what this hides in here. It's hiding the fact that we now know something about what probability means, right? Probability is going to be a number between 0 and 1, inclusive. A probability of 0 means that that is an impossible event. That's actually a dictionary term in the book. An impossible event is an outcome that can't happen. What is the probability that you're going to draw a 7 of stars when you draw the card? 0. There are no 7 of stars in the deck, right? Anybody ever play 5 crowns? 5 crowns is a cool card game, but there is a suit in there. It's usually interpreted as stars.
Have you ever played Jirochi?
No.
It's the 7th tarot deck, and there are the wands.
Yeah, elbow weird. Yeah, yeah. I can tell you a story about that after a while, but we'll wait till we get out of the cards. get out of the lecture. Okay, so an impossible event would be something that has a probability of 0. I don't think your book gives a definition of something that is a certain event or whatever when the probability is 1. That means it'll definitely happen. What is the probability that you'll draw a card when you draw a card? Is the best thing I can think of right there. Or if all 8 of the balls in the bucket are blue, what's the probability of drawing a blue ball? Right? So that's a certain event. And of course then the probability is somewhere between 0 and 1. There are no negative probabilities. There are no probabilities greater than 1. Now, these are all simple events. And the book wants us to at least start thinking about the fact that there could be compound events too, where you're talking about multiple things happening. Like E is drew a spade, and F is the event drew a 7. Those are 2 different things that could happen. I'm going to draw a card. Maybe E is right. I drew a spade. Maybe F is right. I drew a 7. And what we mean by compound event is then we can have like, what is the probability of E and F? Now remember, that's that intersection symbol. And that intersection symbol means like both things happen. Remember, the way to remember that is like intersection, like 2 roads crossing. When you're standing out there in the intersection of First Avenue and Buena Vista, you are in Buena Vista and you are in First Avenue. Right? It's the part that's both. How many ways can it happen that you have a spade and the 7? The only way that can happen is if it's the 7 of spades, right? So that would be, in that case, that there's only one way it could go right, and there's 52 ways it could happen. There's 52 different cards, it's still 1 over 52. Now, let me just take a moment to tell you that that hurts my soul to see that. From a teaching point of view, I understand what he's doing. He's using that intersection symbol to mean and. Just like they use that intersection symbol to mean and when you did sets. You were like set buildings and so on. And that's neat. And from a teaching point of view, that makes some measure of sense because now you're using the same symbol two different ways. I mean, you're building on what you had before. Just so you know, in case I write it wrong, or in case at some point the book changes its mind about that, or whatever, that's actually not the right symbol in probability. In probability, and is actually an upside down V. I get it from a TD point of view. He's trying to reduce the number of symbols he introduces you to, and all that kind of stuff. But I'm not sure you made the right choice here. I think I would have probably just said it's not that big of a deal to know one more symbol. Again, though, it is not a coincidence that they look almost alike. That the upside down U and the upside down V both mean and, just in two different contexts.
So in probability is or just an
It's going to be a regular size V. Yeah, a regular V. Yep. Exactly. So we could have another compound event, right? We could have the probability of E happening or F happening. And again, because it hurts my soul to see that, I like to use the V. I was a stats major in college. I have a bachelor's in stats as well as in atmospheric science. And so it kills me to see them not using the symbol that will be used in other classes. I mean, if you go off to college and you take another class, these U is in so on. But this is the or then. In this case, then, this means you have a spade or a 7. How many ways can that happen? Well, there are 13 spades you might get. Now there's 4 7s, but one of them was already the 7 of spades. You already counted that one. So, but you still got 7 of hearts, 7 of diamonds, and 7 of clubs. So 13, there's a total of 16 ways that can happen out of 52, and then we can do the math and see what that's happening there. But you know what, that one's actually kind of cool, because it illustrates something important. I mean, there I just sort of counted on my fingers to see how to compute a probability when it was an or a union. But that leads us to the so-called union rule of probability. Which is a more general idea. I mean, right there I could count how many times we had a spade, and I could count on my fingers how many times we had a 7. But what if this was something more complicated than that? I mean, we were talking about, something that there were thousands of outcomes. Well, we can still get that because anytime we have the probability of E or F, the probability of E or F will be the probability of E plus the probability of F minus the probability of E and F. That's an important one to know. Because let's look at how we did this before, where we meant E meant spade and F meant a 7. Well, what's the probability of a spade? That was 13 outcomes over 52. What was the probability of a 7? That was 4 outcomes over 52. Hey, let's count those on our fingers. There were the 13 kinds of spades, plus the 4 different 7s. But here's the deal, we've counted one of them twice. The 7 of spades got counted twice. We counted him when we counted the spades, and we counted him when we counted the 7s. So we counted one of them twice. We got to get him off of there. And that is the probability that we have E and F. In other words, the probability that it is a spade and a 7. Well, there's only one way that's going to happen. So it was 13 plus 4 minus 1, which is 16 over 52. That union rule is a super handy way of doing this. Now, hold on a second here. They get sure I don't have it here. Well, if there's a union rule, there are like when you have or, the probability of this or that, it seems like there should be some kind of intersection rule. But it's not quite that simple. In other words, for probabilities where you have and. We're going to have a later section. Where is that? Is it the next one? Conditional probability. That makes that a little bit more clear as to what's going on here. But the intersection rule, as in, like, what is the probability that E happens and F happens, is the probability that E happens times the probability F happens if E and F are independent. And independent is an important vocabulary word here. Independent means one happening is unrelated to when the other one happens. If I had a deck of cards here and a dice, I guess the right word is a die when you're only talking one. Okay? And I'm going to make some silly game. Let's make some silly game here. Let's make a little game where you're the big winner if E happens and F happens, where E is you roll a 5, and F is you draw ace of spades. Okay, it's a game. You come over here, you draw a card, and you roll the dice. And you are the winner if those two things happen. Those two things are independent events. Drawing the ace of spades has nothing to do with the rolling a 5 on the dice. Whatever you get on the card has nothing to do with what's going to happen over here. They're independent of each other. That is not always the case. The probability that it is less than 20 degrees outside and Malia is wearing a coat are not two independent events, right? Because you're more likely to be wearing a coat. If it's 20 degrees outside, it's pretty much a guaranteed deal you're wearing the coat, right? And if it's 90 degrees outside, you're not wearing the coat, right? I mean, these two things are not unrelated to each other, right? This rule won't work then. We will have more complicated rules about how ands work, because they're not always independent. In practice, by the way, this business of the union rule also has independence. How should I put it? It's buried in this term. See, if you're thinking, wait a minute, then isn't this term here, this term that's got an and in it, isn't this term kind of already hiding? If being independent is part of and that's got an and in it, yes. Okay, this has got the same problem hidden in it already. But we'll get there to more. Fortunately, all of the problems that we do at this point are simple examples that are independent. They're going to be things like, you have two different drawers of socks. What's the problem? You reach into the first drawer and you pull out a sock. You reach into the second drawer and you pull out a sock. What are the probability that they're a match? That kind of thing, okay? What you drew out of the first drawer has nothing to do with what you draw out of the second drawer. That kind of thing, okay? They're all independent. This is all going to be fine. It's only until we get to a later day that we start seeing how not being independent can be the big problem here.
So with like your question about the cards, is that considered independent?
Which one?
Your thing about like drawing the 7 and the spade, is that
No. Are they independent? Yes, they're independent. Yes. The suit of the card has nothing to do with what the number on the card is. I can't think of the word for the number. Is this the value or something? Anyway. Yes, those things are independent. You're right. Yeah. So anyway, I mean, we're not, trust me, there's a reason why the word independent isn't like a big bogged down thing on this assignment, because we're not going to need to worry about that very much. Okay? That's actually not going to be where we're getting, it will not be until, like, I think it's either the next section or 2 sections from now that we do that a bunch. Hey, what if we change these? By the way, you can do the math there then and say, well, what's the probability you're going to roll a 5? It's 1 out of 6, right? There's 6 sides to the die, one of them's a 5. What's the probability you drew an ace of spade? It's 1 over 52. So this is 1 over whatever 6 times 52 is. Not very likely. We could have fun with it with the mega ball, the 2 Powerball or whatever the games last night, right? You guys saw this here, Mega Millions and Powerball. Between the two of them, they both drew last night, I think, and between the two of them, it's over $1 billion. Lots of people buy both tickets. You can have. What is the probability you won both games? Probability you're a winner of Powerball and won the Mega Millions, right? We can do that odds. It's a giant number. My in-laws are camping this week, and they called us from their campsite and said they don't sell Mega Millions and Powerball tickets in this state. Please get us one of each before they stop. Because we had to go up to the gas station at like 8:55 last night, and I was like, "This is the saddest thing ever." Anyway, but we bought one of each, so maybe we won both. All right. Hey, if this idea of and. Wait. Let's not use it with this. Let me think about this more broadly. What about we could do probabilities kind of empirically too. For example, we talk about people in this room. There are 2 boys and 4 girls in this room, right? That's what they mean. Your work is going to use that term every now and then. Empirically, we measured that. Okay. So like we counted who's in here. Then we randomly pick a student in this class. What's the probability it's a boy? What's the probability it's a girl? What's the probability somebody on the south side of the room? What's the probability somebody on the north side of the room? What is the probability that the person on the others we draw someone in random? Okay, in case you didn't know, that's south, that's north. What is the probability that we draw somebody at random from this room and they're on the south side of the room and they're a boy? Let's do that. Okay, probability, we draw somebody and they're on the south side and a boy. How many ways can that go right? 2. And out of how many? 6. So there's a 2 out of 6 probability. But we could have done this using that no, we couldn't have. Okay. Alright. Because we can just count this one, right? What? Wait a minute. Wait a minute. Let's try that. Wait a minute. Probability of south side and a boy, couldn't that be the probability you're on the south side times the probability of being a boy? Yeah. Let's see if that's right. So you have 1/2 chances because half of you are on that side times the probability it's a boy is 2/3, and look, it worked. Right? That worked? Alright. What's the probability you're on the north side and a boy?
0.
Why?
Because half of us are on the north side of the room, and there are 0 boys.
Yeah, there's no outcome that works here, right? But what's the probability you're on the north side? 1/2 times how many? What's the probability you're a boy?
0 out of 3.
Well, no, the 2/3. I mean, wait, not 2/3. I did this wrong. Wait a minute. The probability you're a boy was 2 out of 6, so it was 1/6. Do you see what I'm doing here? Wait a minute, something's wrong. It's because being a boy and being on the south side aren't independent, right? If boys were equally distributed every which way, that'd be different. But we already know the dice is loaded, right? The boys are all over here. That's why I'm trying to show you here with this about. But what I really wanted to get to was this one. She said 0. There's a powerful vocabulary word here. These 2 events were mutually exclusive. Mutually exclusive means A can happen and B can happen, but they can't both happen. Right? A is a possibility thing, or B is a possible thing, but you can't have them both. In this case, you can't have randomly picked a student that is both a boy and on the north side of the room. That just doesn't happen. Empirically, we can see it could happen. This is often used in like logic. What is the probability that statement A is true and statement A is false? Well, as long as you're using binary logic and all that kind of stuff, it can't be both, right? What is the probability the switch is on and off? It can't be both. Those are mutually exclusive things. And they're going to throw that word mutually exclusive around a couple times. Mutually exclusive is actually a hugely important idea when we're talking about hypothesis testing, like how scientists decide whether something is true or not. But we're not going to get to that for a while. In fact, we may postpone that until a different course, but that's another story. All right. The point is, we are not going just anywhere too wild with any of this on probability. Now, when I am writing questions about probability, I keep almost making a disastrous mistake. In fact, I do make the mistake and I have to fix it. I almost say odds. Stats majors hate the word odds. Odds is just a mess. It's a perfectly consistent way of writing about things about probability, but it's a messy way of doing it. Strictly speaking, odds has a definition. Like, what are the odds we would pick a... We're going to draw a student at random. What are the odds we would pick a boy? And strictly speaking, the definition of it is the probability that the event will happen divided by the probability the event's opposite will happen. Or complement will happen. So like in the case of drawing a boy by randomly, we would have the probability that that would happen at random is 1/3. The probability it would go wrong is, we would not get him is 2/3. And with a little rearranging here, you can see that the odds are 1/2. What the hell does that even mean? That doesn't sound like... Wait a minute. See how, like, do you already sense the creepiness of odds? Odds is weird. Wait a minute. I know probability kind of makes sense. It means there's 2 ways it can happen out of 6 ways it can't happen. This means that there are 2 ways it can happen to 4 ways it doesn't happen. Right? So we would normally write that as like 1 to 2 odds. Or like if we were just betting on here, like it would be the same as saying like 2 to 4 odds. But you see, I hate that. I mean, they use that in like betting. And they usually only like to use odds when it's more likely to happen than not. Okay? Some political candidate has 7 to 3 odds of winning. Okay? If the candidate has 7 to 3 odds of winning, what that means is there are 7 ways they could win and 3 ways they would lose. Okay? Or another way to think of it is if you know the odds, the probability is like wins over wins plus loses. So in this case, 7 ways of winning over 7 ways of winning plus 3 ways of losing is 7/10. But here's the deal. Once you start thinking about probability, odds just seems dumb. Despite the fact that, like, every stupid sports betting site, they all do it in odds. But that's really, really hard to think about once you know about probability. But your book has a handful of... I don't know that I gave you any homework set problems that involved odds, just because it's kind of awkward. The book does want to show you one more thing. Let's say there are various outcomes that are possible. I am going to pick a student from this room. I'm either going to pick a boy or I'm going to pick a girl. So let's just say B is the event we picked a boy, and G is the event we picked a girl. One thing, if those are the complete set of, that's the whole universe of choices, the book does want you to realize that the probability you pick a boy plus the probability you pick a girl equals 1. Okay? When you add up the probabilities of all the possible outcomes, it needs to add up to 1. Later we'll do more with that idea. when we have more complicated events that have multiple possible outcomes and so on. If you're thinking it looked like I was flipping around a lot in the book and went through 2 sections, you're exactly right. The truth of the matter is 7.3 doesn't actually cover very much material other than this basic idea of, oh, we count how many ways it could go right and then divide it by how many ways the outcome could happen. Alright? So 7.3 is a little bit of not much. And so we don't really need to spend a whole day on 7.3 when we can add 7.4 to it. And so, let me get the lesson plan up here. I didn't post it yet on its learning or anything. Alright. So, now, on this particular assignment, much like the one you did for section 7.1, the truth of the matter is, a lot of these things there's no work to show. Like, it's going to look like this is a lot of math. On page 308, I want you to do problems 19 to 40, which sounds like a lot, but almost all of them, there's no work to show. Okay? I mean, it's just like, you know, they give you, there's a bucket of balls, there's 4 green ones and 8 blue ones. What's the probability you're going to get a green one? Honestly, I can't even think of what work I would make you show. And then I also want you on page 316, which is the next section, to do problems 15 to 20. And honestly, that will be a good enough sample of the kinds of things that we're doing that we'll be ready to move forward into the different conditional probabilities and so on as we move forward. Okay, so why don't you go ahead and get started with that. And we do have an exit ticket, but I'm not sure if I have it posted yet. Let me check on that kind of stuff, okay? All right.